Good afternoon, ladies and gentlemen. I'm glad to see you've all arrived and that your zeal for physics has overcome your desire for a long, leisurely lunch. We have an exciting session prepared for you, a melange of spinning projectiles and ludicrously complicated molecules, and I think 4 very good talks. The first speaker, I would like to remind the speakers, the first 2 will be 25 minutes long. I'll give you a warning at 20 minutes with 5 minutes remaining. There'll be 5 minutes for questions. And then the last 2 talks will be 12 minutes. I'll give you a 2-minute warning and then a 3-minute section for questions. Our first speaker is Philipp Herwig of the Max Planck Institute for Nuclear Physics, who will be speaking on the determination of absolute configuration of a chiral epoxide using foil-induced Coulomb explosion imaging.
Okay, thanks a lot. So what I want to talk about is, in principle, a method to determine the structure of molecules. Normally, the structure of a molecule is determined by spectroscopy, which is, as can be written almost everywhere in every textbook, the study of molecular structure and dynamics through the absorption, emission, and scattering of light. Well, a typical experiment could look like this. One has a light source, a monochromator. Then one shines this monochromatic light through a sample and in the end detects it. And what one gets out of this experiment is then a spectra which could actually look like this. But at this point, theory is needed to understand the spectra, so one has to think about potential surfaces, energy levels, and so on. But if this is then successful, one gets a calculated spectra, and one agrees at this point the 2 spectra, and if they agree, one compares these 2 spectra, and if they agree, then one says, okay, this molecule is understood. Sometimes spectroscopy fails. For some problems in molecular physics, we don't get the answer in principle we are looking for. So this can be the case for a quasi-linear molecule like CH2+. Is it actually bent or is it really linear? Or molecules that are very short-lived and hard to produce, like this example of H2+ I show here. Also, which handedness does a chiral molecule have? This you cannot answer easily via spectroscopy. And at this point, Coulomb explosion imaging can help you and give you provide you with an insight in principle of the molecule. So what are chiral molecules? Just to remind you shortly, chiral molecules exist as a pair. They have the same atoms, but still their structure is different. These isomers are then more or less called enantiomers, which cannot be rotated or translated to superimpose each other. So we see here 2 chiral molecules, which are, because of this asymmetry, then mirror images of one another. In stereochemistry, which is the chemical discipline that deals with these chiral molecules, one uses the SIP rule, which relates then the handedness of the structure of a molecule to its handedness by assigning either the R or the S configuration. We'll come to this later. So this can be, in principle, called R configuration and S configuration. Chiral molecules have different properties. Enantiomers of chiral molecules have different chemical properties in enantiopure environments. And for one example would be the human DNA that only exists in one absolute configuration. The only physical property in which these enantiomers differentiate in is their optical activity. This was actually found out here by Louis Pasteur, who sorted these tiny tartaric acid crystals by hand and also by their handedness, and dissolved them then in a liquid. And when he now shone linearly polarized light through it, through this sample tube, he noticed that the polarization of this linearly polarized light rotates, and that the rotation direction actually depends on the handedness. So one could, in principle, classify chiral molecules by their optical rotation direction, which would be then plus or minus. But which enantiomer has actually which property? This is the question that first troubled Emil Fischer when he developed his lock and key model. But since he could at that time not determine the absolute configuration via this optical activity, he thought, okay, it might be good to have at least an arbitrary assignment as a working hypothesis. So what he did is he took glyceraldehyde. You can see here these two configurations, which are labeled S and R. Again, this is by the SIP rule. And then he assigned arbitrarily the S configuration to have this optical rotation direction minus, and the R configuration to have the optical rotation direction plus. This assignment then has been chemically linked to many other molecules and is up to today still the reference standard for stereochemistry. It took somehow 50 years until this assignment was then actually confirmed via anomalous X-ray diffraction on the sodium rubidium tartrate crystal, and this technique is actually sensitive for the handedness of a chiral molecule, since a phase lag is introduced in one atom by exciting it via energy-defined X-rays. So Byford et al., the authors of this paper, carefully stated that Emil Fischer's convention appears to answer to reality. Up to now, all the measurements of this assignment depend either on Byford or on quantum mechanical calculation. So the goal of our measurement then actually was to test this assignment in gas phase and independent of any molecular theory. And this brings me then to Coulomb explosion imaging, or to be more precise, to foil-induced Coulomb explosion imaging, where we in principle take pictures of single molecules. So how do we do this? We need fast single molecules. Fast means they have to be have a few percent of the speed of light, and we direct them then onto a stripping foil. In this stripping foil, the electrons of the molecule scatter inelastically with the electrons in the foil, and they are stripped off, at least the binding electrons of the molecule are stripped off. And this stripping process is very fast. It takes less than 1 femtosecond, and therefore it is much faster than molecular vibration. So during the stripping process, you can consider like the structure of the molecule to be frozen. What happens then after this stripping is that the charged atoms start to repel each other until they gain, after like 1 micrometer, so-called asymptotic velocities. We then let the fragments 3 meters, give them space to drift apart until we detect them then by the position and time sensitive detector. So typical fragment distance here could be like 5 centimeters or something. From these relative fragment positions, we can then calculate these asymptotic velocities, and by this get an insight of the structure of the molecule. The technique was pioneered by Zeev Vargat here from the Weizmann Institute, and I want to give you at least a schematic description for a diatomic molecule of the Coulomb explosion process. So what happens here is that one takes this the squared wave function, so the distribution of the probability distribution of the internuclear distances, that one reflects them via the Coulomb potential here onto the so-called kinetic energy release axis. And this kinetic energy, we can calculate via these asymptotic velocities, and this works very good, especially for these diatomic small molecules. And the Icpeac, we have performed measurements on H2-, D2-, Hg+, and so on. There were also measurements on H3+ and DCO+, that have shown the potential of this method to really determine also the binding energy angles of more complex molecules. And this then brings me also to the determination of the handedness via Coulomb explosion imaging. So just to remind you, what we measure, this is here are these asymptotic velocities of these fragments we see here. This here is now a three-dimensional picture, so please think about this picture here. This and this fragment come towards you. This here more or less stays in position, and this fragment goes away from you. This is three-dimensional. So how do we do this? How do we determine the handedness? Well, at first, one orders these fractions by their priority. This can, for example, be their atomic number. But this is very well defined via the SIP rule I was talking about earlier. Then, in the second step, we define so-called relative velocity vectors. That means we connect these fragments by their priority. We really follow here the priority ordering. And then we get the handedness via a triple product we call here H. And this triple product is actually positive if we are looking at the R configuration, or negative if you're looking at the S configuration. So let's get concrete. The molecule we were performing our measurements with was trans 2,3-deuterooxyuran. You can see it here, C2OH2D2. Here are the Cs, the O, two deuteriums, and then here we have the hydrogen. This is the R configuration, and on the other side we have the S configuration, and they are, of course, mirror images of one another. The molecule was synthesized by Oliver Trapp of the University of Heidelberg, and it has several advantages for our measurement. It has it's a low mass. That means we get it fast enough to really trigger the Coulomb explosion process. It can be produced in almost an unsuperior sample. That's what we need to really test this Fisher's assignments. It features C2 symmetry, so we have here two Ds and so on. We can turn it around, and so we have a redundant chiral information in this molecule. It can be ionized. This is also what we need to do without any structure changes. And it can be linked to the stereochemical reference standard. Also, again, this we need to test Fisher's assignment. Our setup looked then like this. We have a cold cathode ion source that produces us a singly charged oxyuran. We have a single-ended Van de Graaff accelerator that accelerates the molecule to 1% speed of light, and then, of course, a mass-selecting magnet, which is then followed by several more dipoles before the molecule enters, in the end, this Coulomb explosion imaging beamline. This beamline actually starts with a chopper, which is charged when the first fragment is recorded here on this round detector, and by this we ensure that we only measure one molecular event one molecule at a time. Then after this last bending magnet, we have two collimators. These collimators more or less define us the beam profile. It is followed by a stripping foil, where the Coulomb explosion process is then actually triggered, and from this stripping foil emerge like neutrals, H+, D+, C+, and so on, many charge states and different molecules. So we really have to identify which molecule fragment we are looking at, and therefore we have a so-called ion identification field, again a magnetic field that deflects us the fragments by their charge-to-mass ratio, proportional to the charge-to-mass ratio here in this direction. And then we set the magnetic field in such a way that the H+ are actually guided here. We didn't detect them at all, and the D+, they were solely guided here on this round detector, and then we had like C2+ and O2+ here at very defined places on the rectangular detector, and we can then define identification windows to get information about the fragment. Unfortunately, this doesn't work in reality as good as I've told you now. So if we look here at the plane of the detector, and this here is the C2O2+ detector plane, then you can see here we think that we have C2+ ions Here we have O2 plus distribution of ions, and then a very strong contribution of C plus. So this, we really had to optimize our ion identification procedure because of this problem here. So how did we do this? What we did is we measured and fitted separated charge state distribution. That means we stepwise cranked up the magnetic field, and for example, in a way like this, that we guide only the C plus on the round detector, and this allowed us then to do this procedure. And then we fit our oxyran measurement distribution. That means we set again to the magnetic field to measurement conditions, and then we fitted here this distribution with a superposition of these three other distributions. And if you now look at the contribution of the single distributions that I indicated here, you can define here these two ion identifications windows very good. And in the end, we accepted only events with one hit in this O window here, and two hits in this Z window, and also one deuterium. But of course, you can you see already here that the misassignment is possible. So we performed our measurements. Let's have a look at our data. And I have to explain to you how I want to present this data. So what we did is, for each molecular event, we defined a coordinate system, which looks like this. We put the two C's onto the y-x-axis, the center of mass of the CO, this here is the O-C triangle, on the positive vy-axis, and then we additionally exchanged, symmetrized the position of the detected D, since we didn't know which D we actually have detected. Then we went further and projected the position of the D into this XZ plane, and then the quadrant in which the D lands in tells you, is it the R configuration? This would be then this quadrant of this XZ plane, or the S, if it is the S configuration. We actually measured two samples, a racemic sample and an enantiomer sample. The racemic sample has a mixture of both enantiomers to equal amounts. This in principle was our reference sample, and then we also had the enantiomer sample, where we wanted to determine the handedness of the molecule which are in this sample. And this here is then the density plot of this XZ plane, as I've introduced to you before. Here we see the position of the Ds in exactly this plane, and the numbers I show you here are then the numbers of Ds in exactly the according quadrant. So red number, you can compare to there, indicates R configuration, as blue number indicates S configuration. The racemic sample is by chance slightly asymmetric, but already here the enantiomer sample shows that we have the R configuration of the molecule in there. And also, if you look at these pictures, you already see here very many these. But still, we are dealing with strongly vibrating ions. Since we in principle almost directly injected the molecules from the ion source into our Coulomb explosion imaging beamline, and the molecules just didn't have enough time to vibrationally cool. So we thought about a method to suppress the molecular vibrations, and this we did by considering the area of the COC triangle after the explosions. We simulated the area of a non-vibrating vibrating molecule, and you can see here this is really then a very well-defined distribution. And if we compare it to the measured distribution, you can see that high degrees of molecular vibration will start to reduce this triangular area. So what we did in the end is we accepted only events with an area here lying in this region. I integrated here. Now, if you have a look at our data, we see that the racemic sample is almost perfectly symmetric, and the enantiomer sample, the contrast, of course, has enhanced, and the asymmetry here is now 5 sigma strong, that we are looking at an R configuration of the molecules in this sample. We even went one step further. We tried to suppress, or we also succeeded to suppress misassigned events. And this we did by creating samples of deliberately misidentified events and subtracting these samples. Here I don't want to really go into detail, but as you can see, now we have, again, almost perfectly symmetric numbers of Ds here as we expect, because we are looking here at the racemic sample, and the contrast here enhanced very much. So the result of our measurement was the sample is of R configuration, and we can give also a statistical confidence level, therefore, of 5 sigmas. So I told you we want to test Fisher's assignment with our measurement, and I at least want to give you the logic maybe behind this chemical correlation. So please don't ask me how the chemists did this exactly, but they started off an alcohol somehow, and then synthesized us our oxyren, which is here. And our measurements now determined the handedness of this molecule. And by this, since this chemical synthesis is very carefully done, also the handedness or the absolute configuration of all the other molecules, of the chiral molecules here, is known. Now, one needed a link to the stereochemical reference standard, which is here shown plus glyceraldehyde, and this had to be done since there was no way to for a chemical synthesis directly from this oxyren to this glyceraldehyde. This was then done by an intermediate molecule, and they also did some enantioselective gas chromatography to close this last gap here. So in the end, we could, with our measurement and with also, of course, this chemical network which was developed, confirm that the stereochemical reference standard is correct, and we did this by molecular imaging. This brings me then to the summary of my talk and maybe also future implications. So we developed a mathematical equivalent to this zip rule. We determined the absolute configuration of a nearly enantiomer sample with a statistical significance of 5 sigma, and we then also could confirm Fisher's assignment directly in gas phase. If one thinks about the future, one can also imagine maybe a new setup, and an ion trap in this setup would be great, just to get rid of the vibrations and to cool down the molecules vibrationally. Here I show you the collaboration, also the institutes and so on. I see some of the collaborators in this audience, so it was a great pleasure working with you. Thank you for this great experience. And also I want to thank you for your attention.